Thank you, Kim Young, and thanks to all the organizers for putting together this workshop and asking me to speak. I'll talk about trying to construct effective field theories for open quantum systems with a long-term memory from holography. This is based on a series of works I've been doing over the last year and a half. So the study started a few years ago when I primarily were working on with my long-term collaborator, Logan Igam. But the story started about a year and a half ago when he and I, with the student, Chandan, worked out a useful paradigm to talk about open quantum systems in terms of Schwinger-Keldysh path integrals evaluated gravitationally. And since then, we've been sort of steadily trying to chip away at more complicated systems. So what I will primarily talk about is the paradigm that we developed in a paper last winter with Logan and various postdocs and students, his student Akhil from ICTS, trying to describe how diffusive dynamics, which has long-term memory because diffusion proceeds very slowly and leaves behind relics, can be described in terms of an effective field theory. This is close to my heart because I've been trying to develop with Logan an effective field theory for fluid dynamics. And there was a very nice follow-up work which I did with our postdocs Temple Hay and Julio Virueta. I think Julio is here, where we also showed that this paradigm extends not just to stress tensor dynamics but also to stress tensor dynamics when the stress tensor is coupled to a conserved current, and you can decouple these two things, as I'll explain. And with Julio, Temple, and some other people, we've been trying to extend this to discuss the physics of sound, which turns out to be pretty complicated, which is why there are lots of question marks as to when these papers will actually appear. I was hoping that the first of these would have appeared by now, but as you'll see, there are some subtleties. Okay, so let me start with a big picture paradigm and explain why this question is interesting, why this question is challenging from the point of view of quantum field theory, and what we can use holography for, and why it provides us a useful insight here. So very simple paradigm. So you have some environment, which is some quantum system in its own right. You have some probe system, which is what I will call the probe. And they're coupled to each other by some system environment coupling. So you could just have separated them out in degrees of freedom, but they could be living on top of each other. It could just be some subsystem. The probe could just be some subsystem of some complicated system. The joint system environment probe state, let's say the density operator on E union P, that evolves unitarily like any density operator. But if you trace out the environment and just ask what is the autonomous dynamics of the probe itself, the density operator of the probe doesn't evolve unitarily because you're tracing out the interactions with the environment. In particular, the entanglement characteristics of this density operator of the probe will change as a function of time. In other words, the evolution of this probe density operator is not just non-unitary, it evolves by some generically, it just evolves as a non-unitary quantum channel where the probe density operator gets mapped to some other probe density operator through this quantum channel CE. The CE is a quantum channel that talks about what the evolution upstairs in the system in the environment probe joint quantum systems. And this is not the most general quantum channel. Quantum channels can also take the probe and further trace out degrees of freedom. They just maps from positive operators to positive density operators to positive density operators. So, but I'm just going to focus on quantum channels, which are obtained this way by tracing out some environmental degrees of freedom. Okay. And the question I want to ask is, what is the effective field theory of such quantum channels? Okay. And this is not a question that we are the first to ask. This question has a long history. And the first people who, in my opinion, asked this question and answered it somewhat nicely in the language of path integrals for Feynman and Vernon. And the prototype, which they thought about, was as follows. Let's just give ourselves some variables. Let's say the environment is characterized by some degrees of freedom x, and the probe by some probe degree of freedom psi. And then what we can ask is, I have some path integral over psi and x of weighted by e to the is, and this action involves an autonomous probe action, an autonomous environment action, and some environment probe couplings. This is the path integral you would write down if you're trying to compute quantum amplitudes. But remember, I'm talking about quantum channels, which talk to the entire density operator. So really, quantum channels map probabilities to probabilities. So I should talk about the quantum probability, not the amplitude. So I really need to take this amplitude multiplied by its complex conjugate, and then trace out the environment degrees of freedom to ask what's happening insofar as the probe is concerned. Okay. And if I integrate out the environment degrees of freedom, these x degrees of freedom, and at the level of the density operator on the probe, I'll find that I have the following kind of path integral. I have one set of probe degrees of freedom, which you can think of as the probe degrees of freedom corresponding to Ketz, a second set of probe degrees of freedom corresponding to the brass, so that I need two sets of degrees of freedom to talk about the full operator. So I have a matrix worth of degrees of freedom. And then I have the Ketz evolving forward in time, as Ketz always do, but the brass evolve backwards in time, so there's a overall minus sign. But in addition, I have some coupling between the Ketz and the brass coming from the fact that I integrated out the environment. If there was no environment, and if evolution of this density if let's say the state was to start with pure, then this influence phase would be influence functional as defined by Feynman-Vernon would be 0, and you'd have a factorized action, left-right action for the probe system. The catch is, in general, because you've integrated out the environment, the influence functional is non-zero, and the question we asked earlier about trying to constrain the effective field theory of such quantum channels is really a question of constraining such influence functionals along the lines of what Wilson would have told us for usual path integrals, for usual effective field theories. I emphasize that the standard Wilsonian logic by itself doesn't do the job, because what we have to do is constrain this influence functional not by unitarity or basic quantum field theory rules of this low energy of just the probe degrees of freedom, but rather keep reference to the fact that there was a joint probe environment system that evolved unitarily. So microscopic unitarity is a strong constraint on what the class of influence functionals one has. So before I do this in quantum field theory, let me give you a very some simple set of examples just to whet your appetite, and then we can use that to motivate the holographic setup. So let's talk about linear dissipative systems, which is what Feynman and Vernon talked about. So, and let's just imagine a very simple linear dissipative system, completely Gaussian, quantum mechanics. So my system is a free particle. I could make it a harmonic oscillator. I could just give it a quadratic potential, but I'm not going to do that for now. But my environment is a bath of harmonic oscillators of some number, let's say large n number of harmonic oscillators. And I'll take this environment to be, I'll take these oscillators X to be the thermal state, and I'll take P to be in the vacuum to begin with, the probe to be in the vacuum, and I'll take the system environment to be in a direct product state. The density operator for system environment is basically rho E, which is what I wrote here, the thermal density operator, times the 0, 0 for my probe. And of course, things are not interesting till I start coupling them. So I've coupled them with a linear coupling. So basically, the probe oscillator couples to some linear sum of the environment oscillators. So this problem was posed by Feynman Vernon, who studied some basic aspects of it, but very interestingly solved in early 80s by Caldera and Leggett. So this model typically sometimes referred to as the Caldera-Leggett model, who showed that the probe, once you integrate out the dynamics, evolves by quantum Brownian motion, which makes sense because a probe is like a single oscillator. It's in a bath of oscillators. The bath of oscillators are thermal. The probe basically gets buffeted around by this bath of oscillators. So there's a linear drag coming from the fact that it's in a thermal medium, but it's not just a thermal medium which has linear drag. The thermal medium also has thermal fluctuations. So the effective dynamics is stochastic. So you can just write down very quickly Langevin dynamics for the probe, the effective dynamics of the probe. So there's the sort of huge, since I took it to be a free particle, there's the usual free particle dynamics, but then it's constrained by the fact that this free particle dynamics, due to the interaction with the environment, has friction, characterized by this parameter gamma. But on top of that, there's stochastic noise with some width set by f squared. Okay. I started with the Gaussian system, so noise in this problem is Gaussian. But there's something very important, as Einstein and Samolcharsky explained well near 100 years ago, the fact that the probe talks to the environment, which both buffets it and disturbs it stochastically, means that there is a fluctuation dissipation relation relating this friction with the stochastic noise. And this is the famous fluctuation dissipation relation or detailed balance condition, which says that the expectation value of this noise kernel is related to the friction up to units of temperature. I've put back the mass of this particle. But I wasn't interested in just this classical on-shell dynamics. I was interested in asking what is the effective dynamics as seen by effective action. And you can, in this problem, it's very easy to do, and this was also done in the 70s by Martin C. Jandros and Dominic Spalletti and Janssen in various contexts. And the way to think about it is as follows. There is one dynamical degree of freedom, which is classical, and it would have evolved classically if there was no noise with friction. So let me call that the classical degree of freedom, QA. But there's another degree of freedom, which you can think of as a sort of fluctuations on top of this classicality, the quantum degrees of freedom. And the effective action is not, it has imaginary pieces. It basically has, and it's quite constrained by this fluctuation dissipation relation, but it basically has the following form. It has a classical piece coupled to the quantum piece, and then a quantum piece squared. This classical quantum coupling is really also leading to the fact that you get this part of the action. And the quantum squared, when you integrate out the quantum degree of freedom, you get the noise. If you want to reverse engineer, you start with this action, introduce the quantum degree of freedom as a Lagrange multiplier, and then use the standard Fourier-Popov trick to actually build this action. So in fact, in this action, QD equation of motion is the dynamics of Langevin, is a classical Langevin. So that's what one has. This is the stochastic dynamics of this probe. And now one would like to ask, can you do better? Can you get things like this in more general systems? So let's take that in a couple of steps. Let's just first say, okay, look, you're already in quantum mechanics, Gaussian environments are special. Why should any environment be Gaussian? After all, if you put a probe in a thermal medium, no guarantees that the thermal medium was nice and Gaussian. So there would be non-Gaussian noise. And in quantum mechanics, this analysis is straightforward. Various people have tried to analyze this problem in the last 4 decades. But one piece of work that I would like to recommend is a work done by Loganayagam, which is a former student, Soumyadeep Chaudhary, where they not only looked at the certain class of retarded response, which is a friction response of this probe, but also asking, can you use probes to deduce out of time order dynamics of the environment? And they actually wrote down a 1PI effective action for probes in this general setting. And it's easy to see why this is not so hard in quantum mechanics. Because if you have your system coupled to some probe, and the coupling is through a linear coupling of the with where you think of a classical the probe degree of freedom coupled to some composite environment operator, then insofar as the environment theory is concerned, this probe is just a classical source. So to derive the probe effective action, like we would usually do, you just work out what the correlators of the environment are with Q as a source. So you just write down the generating function of the environment theory for the operators O of X. Okay, and if you want to go to study out of time ordered operators, anything else, out of time ordered correlators, anything else, go to town. There's no obstacle in deriving those at the level of quantum mechanics. So that sounds great, but how do we upgrade all those statements to quantum field theory? Okay, and where do we? What are the rules to imply? And here I'm going to argue that a natural arena to try to start is to start with holographic environments. I'll explain why in a second, but heuristically, various people have made attempts, and I won't give you a detailed list of references here, of trying to come up with effective field theories in, of this kind, starting with, let's say your probe is some scalar field coupled to some other collection of scalar fields, and you try to work things out in perturbation theory. If you do the simplest set of models, there are no problems. You find some sensible answers. But if you start making things a bit more complicated, let's say you add fermions or you add general couplings where the masses of these environment scalars are not commensurate with those of the probe scalars, you start finding various strange divergences and which have not been understood. One heuristic reason why this might be a problem, and I don't think this is the case, but let me just mention it for now, which segues into my motivation for thinking about holographic systems, is that in a generic weakly coupled quantum system, the time scales for thermalization, for time scales for disturbances to propagate is very long. Things don't equilibrate very quickly. So it's nicer to ask questions if you want to ask general properties and have control in terms of environments which are strongly coupled, where disturbances decay away very quickly. Okay? So especially if you have systems which are maximally chaotic and have fast scrambling physics, then those are ideal environments to probe and write down probe dynamics. Okay, so that, roughly speaking, for me motivates holography. I would say that at some day we would like to understand the statements away from holography, but I think that the general structure should also be made completely clear by just looking at holographic models. So let me, before I jump into quantum field theory, let me say that already this Brownian problem can be very nicely studied in this Brownian oscillator, can be very nicely studied in holography. And this is something that some of us worked on well nigh 13 years ago. So you could basically do the following. You could take your favorite holographic field theory. Mine happens to be N equals for super Yang-Mills. You could make it a thermal plasma. And then you could just put a probe external quark in this thermal plasma and ask, how does it behave? It's like you have a thermal plasma, you have a probe quark. The probe quark wants to, if you try to kick it, it wants to sort of drag. So it sort of slowly, it sort of loses energy to the plasma, but it also fluctuates randomly. So if the quark, when you put it here, even if it sort of doesn't have initial velocity, you'll see that it undergoes stochastic Brownian motion where it sort of jiggles around this plasma. Okay, so, and the rough qualitative picture is the following. The induced geometry on the string world sheet, because the classical string just dangles straight down from the boundary. So the quark in ADS-CFT is dual to a string. The string dangles straight down from the boundary into the black hole. And on the world sheet, one has an induced 2D black hole geometry. This black hole geometry has a horizon on the world sheet, and Hawking quanta are basically propagated up this world sheet from the space-time horizon onto the quark, and they are the buffets which lead to the stochastic motion. Okay, and if you try to drag this quark at finite velocity, the string will trail behind, This is the famous dragging sink solution that Steve Gapser discovered well before any of these works. And various people have tried to study the system and use general relations from it, of thinking about the Hawking quanta associated with this black hole, worldsheet black hole horizon as the fluctuations, whereas the classical decay of stuff falling behind the horizon, the quasi-normal modes, is the friction in this problem. There was a nice recent progress, and this is again something that was done by Logan and various collaborators in a paper 2 years ago, where they systematically derived, at least in the now not just for OTO, not for OTOs, but for a certain set of retarded response correlators, which I will explain. They derived the effective field theory of the Brownian particle, now including non-Gaussian noise. So it's not like Caldera-Leggett, where the noise was just Gaussian and that was it. They actually derived the dynamics for the non-Gaussian system. And it's something that I've been working on with a former undergraduate student on trying to understand how this works in rotating ensembles. Okay, so that set of motivational ideas, I hope, gives you whets your appetite for asking, how do we do this in quantum field theory? So I'm not going to talk about the quantum mechanical problem anymore. I was just using that as a orientation for what we want to do. So now let me define my problem in some detail. So let's start the same kind of setups: probe environment couplings. The main ingredient I'm going to use is my environment is a holographic quantum field theory, which I will take to be in a thermal state on Minkowski space, d-dimensional quantum field theory. The coupling between my probe and the environment will be some probe effective operator, coupled to a single trace gauge invariant operator of the holographic quantum field theory. So if you have n equals for super Young Mills, this is just some single trace gauge invariant operator, say trace h squared, or stress tensor, or charge current, what have you. Okay, I'll discuss many of these things as we go along. If you want some heuristic for how to think about this, you can think about this in the language that Faulkner and Polchinski argued for, the so-called semi-holographic model. We are basically going to use holography and thermal correlators in holography as our proxies for building the effective field theory of this probe site. So the couplings of the effective field theory will be dictated by the correlators of OX, thermal correlators of OX. So all we really need is real-time thermal correlators from holography, and we want to ask, how do we apologize for the typo, and we want to implement real-time boundary conditions for semi-classical gravity. Now, this problem itself has a lot of history. It goes back to early work of Son-Starinets, Herzog-Son, almost 2 decades ago, and some important work done by Skenderis and Van Rees, and especially Van Rees from 2008, and various correlation functions in n equals for super Young Mills plasma were computed by this group 10 years ago. And I'll say something that happened in a few years ago that upgraded all these discussions into a form that makes this analysis very clean and very similar to usual ADS-CFT analysis. So we want to do real-time physics, and we want to understand how density operators evolve in a thermal state. So we started with a thermal state. So my thermal density operator is rho beta. And I want to compute correlators by insert of various operators in the environment. Remember, the probe is now a proxy. So for most of the discussion, the probe won't enter. Whenever the probe enters, I'll tell you where it enters. So I'm just for now going to focus on computing real-time correlators in the holographic setup. So I have various environment operators at various times, and I'll compute correlators with a very particular out-of-time order. Okay, so if you look at an endpoint function, let's say I've written here a 3-point function, ignore my dots. The 3-point function has 6 time orderings. T1, T2, T3 can have various time orderings, and there are three operators, so they have three factorial time orderings. 4 of those are special. They can be computed on correlators where you evolve forward and evolve back and go back to your initial state. 2 more are more complicated. They need to be computed on contours which go forward and back twice. just think about how Heisenberg evolution works in quantum mechanics, and that tells you how many folds you have, time folds you have in your quantum path integral. So I will focus exclusively for the rest of the talk on Schwinger-Keldysh path contours. And I want to ask, if I have a boundary holographic field theory, for which I want to compute Schwinger-Keldysh correlators. So on the boundary, I'm prescribing a time contour of the following form. Time is therefore complex. The real time is running this way, and imaginary time is running up. So I go out in real time, take an excursion by minus epsilon, go back in real time, and then go beta minus epsilon back down. And then the initial density matrix, these 2 points are identified because Euclidean time is periodic with period beta. So what the usual rules of ADS-CFT say, what are we supposed to do? Well, we're supposed to take this boundary contour and find a gravitational saddle that fills this contour for us. Okay, so if I gave you the Euclidean time circle, you would say that, since I'm talking about field theories in Minkowski space, you would say, well, just take find a Euclidean saddle point of semi-classical gravity that has a boundary S1 cross RD minus 1. And there is one, which is a cigar, and that cigar gives you the Euclidean saddle. Now, I've taken the Euclidean time contour and disturbed it by adding a forward-backward time evolution. So what I should do is I should split open the cigar and glue into real-time sheets of the geometry that straddle out from this t equals 0 and t equals minus epsilon and meet up somewhere. Where do they meet up? Well, in general, they can meet up on some hypersurface in the bulk. But for simplicity, I'm going to allow them to meet up at future infinite time. This time doesn't need to be future infinity. This time can be the latest time after my operator insertions. And I'm going to take this surface to be a smooth surface that basically encircles the horizon of the black hole. It's better to think of this picture in a Penrose diagram. So here are 2 copies of the Schwarzschild ADS Penrose diagram, dual to a conformal field theory at finite temperature. I'm not going to keep both copies of the Penrose diagram en masse. The forward contour of the Schwinger-Keldysh is on the boundary is this piece of the boundary running from t equals 0 to say infinity. I keep the future half of this domain of dependence with the bulk time running forward this way. And as I fall through the horizon of this piece of the geometry, I come out on the other side in this other Penrose diagram. So what I have is a 2-sheeted geometry, which is what I've tried to depict here, that you go around the horizon smoothly, whereas here I've just drawn it as if I'm just gluing 2 pieces. All this other stuff which is not shaded in these Penrose diagrams doesn't exist as far as I'm concerned for these calculations. Okay, so for full disclosure, this is not the Thomfield double. This is a Schwinger-Keldysh contour, and this is what was proposed by these folks, Crossley, Glorioso, and Liu in 2018. As I said, there was earlier work which precedes some of this, but I think these guys gave the most cleanest presentation of the statement that is helpful for some of the things I'm going to say. So we could work with this 2-sheeted geometry, complex geometry, because time is complex on the boundary, it's a complex time contour. But there's a much nicer way of saying everything in terms of a single coordinatization of the geometric picture. So what I'll refer to this geometry as the GRSK geometry, and it's defined as follows. It's a 2-sheeted space-time with a specific branch cut structure, which encodes the physics of thermal state. So I've written the metric in a very particular form. So this is the metric you can start with a Schwarzschild metric in ingoing coordinates. If it was ingoing coordinates, this would be 2 dVdr. I've just changed things out here so that I've defined instead of a standard tortoise coordinate, I've defined a complexified tortoise coordinate, which I've called the mock tortoise coordinate, which is basically dr over r squared f, standard tortoise coordinate, with some factors, phase factors thrown in. Okay, so that this is done so that the monodrome is, so f has a simple 0 at the horizon, and zeta therefore has a logarithmic branch cut. I've chosen the cut to run from the horizon out to infinity. The zeta coordinate, the contour of integration in zeta basically goes around the cut and picks up 1 unit of monodrome. That 1 unit is what dictates this 2 over I beta. Okay. Beta is the inverse temperature, the Hawking temperature of the Schwarzschild black hole related to the horizon size. Thus, the claim is the following. Start with the Schwarzschild radius geometry, rewrite it in ingoing coordinates and work and convert the ingoing coordinates to this mock tortoise coordinate. That gives you a particular branching structure around the horizon. And this region is going to be important because things are going to pick up monodromies as we go around. And real-time correlators are computed by using the usual Gapser-Klebanov-Polyakov-Wheaton rules or Wheaton diagrams on this geometry. Okay, there are 2 boundaries to the geometry, one here and one here, which you can think of as the Schwinger-Keldysh left and Schwinger-Keldysh right boundaries. And when I need to cut off the space-time, I'll cut it off at large R and then take the limit R goes to infinity. Okay, so you can think of R goes to infinity plus minus I0 as the left/right boundaries of the gravitational Schwinger-Keldysh geometry. Okay, so that's the setup. So now what can we do with it?
Sorry, Mukund, can I ask a question?
Of course.
So why you encounter this imaginary metric here? So usual tortoise coordinate is of course real values. Are you considering some Euclidean continuation?
Well, yes. So just let's go back here. So the usual tortoise coordinate is real, of course, but I need a 2-sheeted geometry that the sheets are glued at an extension of the horizon. So you can think of the tortoise coordinate as going, say, from here to here, but it needs to jump around the horizon and come back to the other sheet. Okay, and usually what you'd have done, and this is usually what's done, is if you think about the turbo field double, you'd say, okay, here you start at Euclidean times 0, and then you fall in, encounter the neck of the Einstein-Rosen bridge. You go around and you come back out to the other boundary, and that's a beta over 2. Imaginary time beta over 2. So it's like I start here and I end up here. But I don't want to do that.
Yeah.
Okay, I just want to come around. So and that coupled with something clever that's been made here is I want to pick up thermal monodromies. Okay, thermal monodromies are nicely taken care of by putting this.
It's kind of moving from one side of eternal black hole to the other side. It's some kind of complex shift.
Well, okay. No, it's not moving from one side to another side. It's moving from one half of an eternal black hole to another copy of another eternal black hole. Okay. If you do what I said before of going from this side to this side and then making it complex, you will get the double cone geometry of Saad-Schenker-Stanford. This is what I'm talking here is not the double cone geometry. It's very important. It's not the double cone.
Same side, but it's going up.
Exactly.
Thank you.
Okay. Any other questions while we are paused? All right. So that's the geometry, and what can we do with it? So let me describe what we first tried doing in the first paper with Chandan and Loga. So for now, let's just take this operator of the environment, the holographic operator, to be a scalar conformal primary of dimension delta. Now, I have chosen to write the GRSK geometry in a manner that breaks the obvious time reversal symmetry of the Schwarzschild solution. T goes to minus T is a symmetry because T is an isometry. In fact, it's a hypersurface orthonormal isometry, but there's a relic of it, which is a Z2 time reversal in evolution, where the infalling time V gets shifted by I beta zeta. Okay, usually it would just be V goes to U, but since I've if you think of VST plus R star and UST minus R star. So we can adapt to this time reversal in involution by working with a natural basis of tangent and cotangent spaces that are time reversal covariant. And for that, let me introduce an operator D plus, which is R squared F d by dr plus dV and correspondingly minus. Okay. The nice thing is the following. You can show that if you look at the bulk dynamics of the field dual to this operator of dimension delta, so some field of mass d delta times delta minus d in ADS, you can write its wave equation in infalling coordinates in this very nice form in terms of this operator D plus, this time reversal covariant operator. And we can solve the problem that everybody has solved for the last 25 years, which is to solve the problem for quasi-normal modes, which is fixed normalizable boundary conditions in infinity and infalling boundary conditions of the horizon. So I can find what I will call the infalling bulk to boundary Green's function by normalizing it with a source appropriately and asking it to be regular at the horizon. So that will give you some Green's function, which we can compute as a function of this Mock-Tortes coordinate and have Fourier transform to frequency domains by just working with e to the I omega v minus I omega v plus ikx. Okay, because I have time translation and spatial translation invariance of my boundaries here. Now, this is related to Tadashi's question. The GRSK geometry has two boundaries. So I need to prescribe data on two boundaries. And the good thing is, by writing things in this time reversal covariant form, you can actually work out what happens to the time reverse solution, not just the infalling solution, but the outgoing solution. You can show that the outgoing solution is the ingoing solution with frequency reversed with a monodromy factor. And this monodromy factor is important. This e to the minus beta omega zeta says that the bulk gravitational solution knows about what monodromy you need to pick up as you go around the horizon. So you can write down the full solution of the scalar field dual to the operator of dimension delta as some infalling Green's function plus some combination of infalling and outgoing Green's functions, which I've chosen to call the Hawking Green's function. Okay, and if you put all the factors together and just study this wave equation and the factors e to the minus beta omega, you'll find, and remember that in my conventions, there was one unit of monodromy going from one boundary to the other. The real part of zeta went from 0 on one boundary to real part of zeta being 1 on the other boundary. So going from one boundary to the other gives us factors of e to the beta omega, which is exactly the kind of statistical factors you want for thermal state. Okay, so what you find, and this is a nice propagator you can write down, this particular linear combination is the Hawking propagator, which is the correct propagator with appropriate statistical factors multiplying. Okay. The second good news is once you've solved the problem, so I emphasize the way you're solving the problem is you're first solving the infalling problem that everybody solved in many decades of ADS-CFT. You're using the structure of time reversal to build the full gravitational Schwinger-Keldysh solution with two boundaries at zeta at r going to infinity plus minus I0. And we can now, having solved this field, we have the full in bulk to boundary propagators going from one boundary to the other. You can now convolve these bulk to boundary propagators, or if you want to compute bulk to bulk exchange diagrams, you can correspondingly solve for similar bulk to bulk propagators. And any Witten diagram which you would want to draw in this picture, you would draw by taking sources here and sending them into the bulk to interact and integrating over this bulk interaction vertex. Okay, so standard Witten diagrammatics, but not on the usual Euclidean ADS geometry, but on this GRSK geometry. Couple of nice things to know. This GRSK geometry only cares about two pieces of the black hole solution outside the horizon. There is no integration in the domains near singularities. There's no integration in the second asymptotic region of the eternal black hole. And these are all necessary for the answer. These are all, in some sense, mandated by the fact that we are talking about real-time physics, but also nice to see that they explicitly work out this way. So with that data, we can just try to find the, so once we convolve these bulk to boundary propagators, you'll be left with one contour integral over this zeta coordinate to do, this mock tortoise coordinate. Remember, this mock tortoise coordinate has a branch cut. So when you do this integral, you can do this integral as a usual cut integral. And what would you get? You're jumping across a contour runs across a cut. So usually the cut integral will just pick up a discontinuity across the cut. So you pick up the discontinuity, which is what I've tried to write for any function f as a zeta, value at zeta plus 1 minus value at zeta. But once you have this discontinuity, once you picked up the discontinuity, you can write this as an integral over a single sheet, just from the horizon to infinity of the discontinuity. So in other words, you solve the ingoing problem, construct after picking up monodromies, all the Green's functions, and all the correlation functions are simply obtained by integrating discontinuities across this cut of bulk to bulk boundary propagators. So here are some results. I'll just flash them for you. So you can easily check that, for example, it gives you the correct correlation functions in a 2D CFT by just in BTZ, you can just compute all these Green's functions explicitly. So this is something we did. And you can check that it gives you the correct fluctuation dissipation relation, because remember that the quantum, which is the DD part, is related to the classical part, AD part, up to a Bose-Einstein factor. And indeed, you just recover that straight up. You can do something similar in higher dimensions, except that now the Green's functions are hard to obtain because it's hard to solve the wave equation in the ADH-Schwarzschild background, unlike in BTZ. But you could just solve them at low frequencies and low momenta compared to temperature and try to derive an effective field theory. And I'll now say the answer for that of that calculation in terms of the probe dynamics. Okay, so now I'm translating all these correlators into an effective field theory for the probe. So my size are back. And here's the answer for the probes written nicely in analogy with the Lagrange dynamics as a stochastic effective field theory. So there's some kinetic term, there's some spatial gradient terms. They don't have to be the same because now we're in a thermal medium, so Lorentz symmetry is broken. So K and D don't have to agree with each other. There's a friction term coming from the fact that the field is now, some part of the field falls behind the horizon, and therefore there is loss, classical loss from the quasi-normal modes. And then there are lots of fluctuation terms, including non-Gaussian pieces of various kinds. So we've computed this for contact interactions. We didn't do exchanges, but in principle, one can do exchanges. And you see that you recover the standard fluctuation dissipation relation. The fluctuation piece, the Gaussian fluctuation piece is related to friction, but you also get nonlinear fluctuation dissipation relations, which were earlier derived for the quantum mechanical problem by Loga and friends, but you also get something similar in the other level for quantum field theory. So this, as far as I know, is the first time nonlinear fluctuation dissipations were derived in a quantum field theory straight up. Okay, so that's nice. So it says that yes, we can do open quantum systems, but there's a problem, and the problem is black holes can remember. So so let me remind you of something that some of you might know. If you look at a thermal plasma, the friction which I got here in this gamma came from the quasi-normal modes, came from the fact that classically field modes disappear beyond the horizon. They damp away. But there are two kinds of operators in thermal holographic plasmas. And I'm going to call them Markovian and non-Markovian for the following reason. The first Markovian kind are ones whose quasi-normal modes are gapped away from the horizontal frequency axis by an amount set by, let's say, temperature or some other parameter in the problem, some other energy scale. But there are some operators like the energy momentum tensor or charge current or any other conserved operator where there exists, in addition to such gapped operators, an ungapped operator, a modulus, which has a quasi-normal mode at nearly zero frequency, at close to zero momentum. In fact, the definition which I'll give for hydrodynamic quasi-normal mode is that omega goes to zero as k goes to zero. And these modes, for example, dictate momentum diffusion in the plasma. So omega goes like minus id times k squared, where t is related to shear viscosity, which is related to entropy density, famously by the Koch-Thun-Sarinets formula by 1/4 pi. Or there's also modes corresponding to phonons, physical phonons of the plasma, the sound propagation, where omega goes like speed of sound times k plus attenuation pieces. And this was pointed out also 2 decades ago by Polycastro-Son and Sarinets. Now, suppose you couple your probe to such a conserved current. The conserved current correlators have poles. They are not local in frequency space. Therefore, in other words, they have long-lived quasi-normal modes, which are Goldstone modes. So if we integrate out such Goldstone modes in trying to derive an effective field theory for the probe, all hell breaks loose because these are not local. There's no such local effective field theory integrating out moduli. So what is the right Wilsonian effective field theory? Retaining moduli when you have such non-Markovian degrees of freedom. That's the question. And there are lots of challenges along the way. So let me explain the challenges by picking a simple example, which is easy to understand. So think of a conserved current probing a thermal plasma. So this current is the background has no charge, so it's an uncharged background. It's a neutral background, and I just take an abelian conserved current. Let's say in n equals for Sophia Mills, I take the thermal state and I pick one U1R piece out of the SU4R current. Its dual in the bulk is a Maxwell field, and there's a source operator coupling as usual, J times A. Let me decompose this gauge field into harmonics under a little group, which is SOD, SOD minus 2. So I pick a direction of momentum propagation, which I've drawn here as K, and I pick the little group on the plane perpendicular to this direction of propagation. I can then decompose my gauge field into modes under SOD minus 2. I'll get some scalar modes and I'll get some genuine vector mode, transverse vector modes. The transverse vectors contain physical photons, which are short-lived. They'll fall behind the horizon, they'll just damp away. They're actually charge transport modes. But the scalar modes, looks like there are 3 of them, but there's only 1 degree of freedom because they're related by gauge invariance, and they actually lead to a long-lived charge diffusion mode. It's exactly like the dynamics, the quasi-normal mode dynamics is exactly like this. Omega goes like minus I times something k squared, where something is basically charge conductivity. So, and this is true not just for the charge current, it's true for any other conserved current, like say the energy momentum tensor. Such currents have both Markovian and non-Markovian degrees of freedom. Okay, So you have to figure out how to separate them. You can't just talk about the dual operator en masse. Second, if you look at the radial, these conserved currents on the boundary correspond to gauge invariance in the bulk, like the Maxwell field in the bulk, which has Maxwell-Gauss law. And the radial Gauss constraint, or the radial Hamiltonian constraint for gravity, says that if you put Schwinger-Keldysh operators, the difference operators are put on shell. So you're losing 1 degree of freedom. So in the paper I mentioned by Crossley, Glorioso, and Liu, they took this mode off shell in a particular ad hoc manner to grab an effective action. I'm going to say we're not going to do that because we're going to try to follow our nose and work with appropriate gauge invariant variables, decouple the Markovian and non-Markovian degrees of freedom, and show you what we get. So the claim is the following. Decompose in this SOD minus 2 reps and take that seriously. And then some very nice magic happens from gravity. You can repackage the dynamics of all such conserved currents into a collection of objects, which I'm going to call designer scalars. So an example of the Maxwell field, the transverse vectors, one which are d minus 2, 1 per polarization index, they all map to some scalar problem. They all behave similarly once I sort of forget about the polarization index. And the collection of the 3 degrees of freedom, naive degrees of freedom in the scalar sector, they map to a similar such object. In fact, they're related in this case by a parameter. I'm labeling a parameter M, which I'm going to call the Markovianity index. And both these fields satisfy a very similar equation. They satisfy an equation with M and minus M respectively, which is like a scalar wave equation with funny powers. This power would have been d minus 1 if we're talking about a standard minimally coupled scalar field, but it's no longer d minus 1, it's some M. And it turns out that for the charge current, this M is d minus 3, but you see that you get a plus d minus 3 and a minus d minus 3 in this problem. So let me explain that in more general. So this is the claim. So whenever you decompose bulk fields, duals to boundary operators with both Markovian and non-Markovian degrees of freedom, you will decouple them, and the decoupled sectors are characterized by designer scalars. These designer scalars are like massless scalars, non-minimally coupled to the background geometry, with a dilaton, which is a non-trivial function of radius. And I can tell you very quickly what the difference between the two sets of degrees of freedom is from this picture. The Markovian guys have a coupling which repels them from the boundary. So the coupling grows rapidly as you go towards the boundary. So the field doesn't penetrate and can't make it to the boundary. The non-Markovian couplings basically decay away to 0 near the boundary, which means the non-Markovian fields are floppy. They can live arbitrarily long near the boundary and have some reluctance to fall in and decay away into the horizon. Hence, long-lived quasi-normal modes. And you can characterize both of them by just saying, as you go to infinity, there's some power law behavior, and that power, the index M, dictates whether you're Markovian or not Markovian. In fact, there's a slight subtlety. If the index is bigger than -1 and the field is quantized with Dirichlet boundary condition, it's Markovian. And if the index is smaller than 1 and has Neumann boundary condition, then it's not Markovian. The interval between +1 and -1 is a bit complicated because it's like a field that's close to Brighton-Lono-Friedman bound, which can be quantized with either boundary condition in areas. Okay, so let me give you a quick summary of how these decompositions work. This was something we worked out in various papers. So if you look at Einstein-Hilbert dynamics with the usual Gibbons-Hawking boundary conditions, so stress tensor is dual to boundary gravitons. So boundary gravitons are sources for bulk boundary stress tensors. The transverse traceless tensors are Markovian. They're d times d minus 3 over 2 of them. And they have this index being d minus 1. Transverse vectors are not Markovian and actually correspond to momentum diffusion. That's what we worked out in the first paper from a year ago. And the scalars, which is what we're working on with Julio and Temple and others, is non-Markovian. There's a sound mode, but there's a very complicated story having to do with soft modes in this problem, which I won't say in detail now. And each of them comes with a definite boundary condition, which is inherited from rewriting these dynamics in terms of these designer scalars. So I'm not putting in these Neumann boundary conditions by hand. They show up from these dynamics. And and you can do this not just for neutral black holes, you can do this for charged black holes. This is the other paper we wrote with Temple and Julio, and we're working on this with them for the scalar sector as well. So if you do Einstein-Maxwell theory, you get a similar set of transverse traceless tensors. You get some transverse vectors, but now you have more of them because you have transverse vectors both from gravitons and from photons. Part of them are Markovian, part of them are non-Markovian. And you have scalars where there's a mixing between charge diffusion and sound. They can all be decoupled, and this is what we showed in this problem. This problem has a very much more complicated branch structure because there's an outer horizon which is here, and inner horizon which is here. And it turns out that there's another locus where you find some singular behavior, which is between the inner and outer horizons. I had not known this, but I don't think this was understood before our paper, that there is actually a locus between the inner and outer horizons that is dual to the charge conductivity. Kim Yong, how much time do I have?
Oh, you have about 3 minutes. Well, I guess you can, there's no talk after this, so you can may have 5 more minutes.
Okay.
Just 3.
Thanks. So now let me package all of this information into, so this is at the level of just classical gravitational dynamics, repackaged into these designer scalars. Now, as I said, these non-Markovian modes are floppy near the boundary, but the Markovian modes are just repelled from the boundary. So you can study the zero mode solution, but zero frequency and zero momentum, and you'll find that the solution comes in 2 forms. There's an analytic mode, which is set by sources. And there's a non-analytic mode with a branch cut coming from integrating 1 over f, the piece involving the mock tortoise coordinate, that is proportional to the difference of the sources between the left and the right. And this needs to be controlled because you want a regular solution on the gravitational Schwinger-Keldysh background. You don't want to pick up monodromies and branch cuts. So it turns out the right way to solve the problem is as follows. So for Markovian problems, we fix the sources on the left and right boundaries. So something like a double Dirichlet problem. And we evaluate the generating function of correlators. So I just fix the field values on the 2 boundaries. That gives me the left source and the right source. And then I find the Green's function from, as I said before, using the ingoing and the Hawking-Green's function. But for the non-Markovian modes, this is not possible. The solution diverges because when m, let's say m is negative, it's less than -1, this solution diverges near the boundary once I turn on this difference source. And that's reflected from the fact that there is no potential barrier for this field to sort of have a large wave function support near the boundary. Non-Markovian fields are so poorly coupled near the boundary that they can just live there forever. And as a result, if you try to compute a 1pi generating function by fixing the sources, you will get a non-local 1pi generating function. So we should not compute a 1pi generating function. You should just Legendre transform that to compute a local Wilsonian object. And the right thing to do turns out to be fix the expectation values of the dual field. So if I have the Markovian, non-Markovian operator O, I should fix its wave and solve the problem parameterized by these waves, as if you were doing Neumann boundary conditions. But I told you the Neumann boundary condition is what is inherited from the gravitational dynamics. There's a fun fact that the non-Markovian Green's functions, you can actually obtain them by analytically continuing the Markovian ones. So this is a nice fact. You don't have to solve the problem twice. And once you've done this problem, the gadget you want to compute is the following. You want to compute a Wilsonian influence functional parameterized by Markovian sources and non-Markovian bits. And it takes a very nice form. It takes the form of at the Gaussian order, where the only data you need, the structure in terms of A's and D's, the sources and bets, is completely constrained by KMS relations and Schwinger-Keldysh unitarity. So this is really what we were looking for. The only piece of data that's missing, which you have to solve equations for, are the Green's functions. And here, this is the infalling or retarded Green's function of Markovian modes. And for the non-Markovian stuff, this is because we've done Legendre transform and gone from Green's function to from the Green's functions to the Wilsonian object. This is the inverse Green's function. It's because these parameters are field values. So this is like the inverse propagator. And with Julio, we've been working out some simple toy models to actually understand non-Gaussian effects, which I won't talk about. So in the last minute, let me quickly tell you some results, tell you that this is not something that we've been doing for fun, but you can actually recover many things that are known and many things that were not known in the past 2 decades. So we have results for various black holes in various dimensions, but here's something which is very concrete. Just look at n equals for Super-Yang-Mills stress tensor coupled to some probe operator. And this Wilsonian gadget, this Wilsonian influence functional, is parameterized by boundary metric components for symmetric traceless transverse tensors, the momentum flux operator corresponding to the momentum diffusion mode of gravitons of stress tensor, and the sound mode corresponding to physical energy propagation, energy transport. At the Gaussian order, everybody doesn't talk to anybody else, so you just can split them. So there's a piece coming from the background, which I'll call the ideal piece. There's a Markovian tensor sector, there's a momentum diffusion sector, and a sound sector. This ideal fluid part is something that recovers a conjecture that I had made with Loga and my student Felix a few years ago on what the ideal fluid dynamical action coming out of gravity should be. So we just recover that at linear order in amplitudes, leading order in linear gravity from the solution. And we have predictions for the Green's functions and inverse Green's functions of Markovian and non-Markovian operators respectively, which agree with everything that has been computed in literature so far. So for example, for the tensors, we get the sort of standard dispersion relation that was computed. For the vectors and scalars, we get basically sounds, momentum diffusion and sound propagation. And I think, so let me summarize. So I haven't translated this last bit of result in the language of the probe dynamics, but it can be easily done. We just have to upgrade, sort of rewrite all of these guys in terms of the probe operator, which I had called chi. Okay. So let me summarize. So holography provides a useful paradigm for developing open effective field theories. In fact, I think the structure of the open effective field theory that holography dictates is universal. The details of what couplings enter these effective field theories will depend on what kind of microscopics we have, whether the environment is holographic or not. But the nice thing that holography has going for us is that we can deduce the structural aspects without going through all the nitty-gritty details. I also want to point out that if you were thinking directly from the point of view of field theory, it's very hard to see what disambiguates long-lived and short-lived modes of conserved currents. You can do this at a level of Kubo formula at various levels, but as far as I know, even in kinetic theory, this has never really been carried out successfully. But there's now a paradigm coming straight out of gravity. And this paradigm is actually quite nice, especially when you have complicated things like a charged plasma where you have some modes which are Markovian, which are talking to some modes which are non-Markovian in the same sector. So it's not like in the neutral fluid, different sectors just decouple from each other, but in a charged plasma, even in the same sector, you have two kinds of modes. Charge current wants to dissipate, momentum current wants to diffuse. So momentum current drags charge current and leads to long-lived behavior in it as well. But you can decouple the two effects at the quadratic order, and gravity tells you how to do it. And one can study systematically non-Gaussian features in these problems. Okay, there's of course much more to be done. I think these are just early days, but I think it's already very promising as far as I'm concerned. And we should be able to find nonlinear solutions extending fluid gravity to include not just the linear response part, but the response part where if I say, I would say that in the fluid gravity solutions some of us wrote down 15 years ago, we wrote down just the infalling, we wrote down the expectation, we wrote down solutions parameterized by the 1-point functions of the stress tensor in the infalling sector. We didn't talk about the fluctuations. We didn't know about what thermal fluctuations were doing. We now have in the GRSK geometry, at least the linearized level, once we put all the pieces together in these various discussions, the linearized fluctuating fluid gravity solution. There is question of how to do Schwinger-Keldysh in gravity more generally away from these equilibrated thermal states. How do we do this in non-equilibrated states? That's an open question that I think is worth thinking about. And there's a more general question, which is how do you go beyond Schwinger-Keldysh? How do you write down effective field theories? As I said, in quantum mechanics, there already exists an effective field theory that talks to for the Brownian particle that extends the usual Langevin discussion to include out-of-time ordered observables and so on. And we don't have such a framework yet available for quantum field theories in higher dimensions. So with that, let me stop and thank you for your attention.
All right, thank you, Mukund. So is there any question?
Can I ask a question?
Sure.
So I think in your analysis, you are most example, you are fixing temperature.
Yeah.
And but on the other hand, we know also solution of black hole which is evolving, like temperature also time dependent. And can you apply your formalism with this some complex value technique to such a time dependent black holes? Or more general time dependent background in ages. There are many, I think, known solutions of time.
Yes. So that's this question. I've been talking about this with various people, but we don't have an answer yet. The question is the following. Let me translate. It's related to your earlier question, Tadashi. In the thermal background, I know how to pick up the monodromy going around the horizon. So if you have a time-dependent horizon, let's say as a simple example, something like a Vaidya geometry, where the horizon is evolving and coming out towards you, I need to pick up some time-dependent monodromy in infalling coordinates. We don't have a good prescription for it yet. I mean, my answer is there should be a sensible way of thinking about it, and we should be able to understand how to do this. Part of the reason why we are sort of playing with these various examples is basically to build up a sufficient intuition of what's happening to be able to do something of that kind.
So your complexified metric also satisfies Einstein equation?
Yes, locally it satisfies Einstein's equations because it just, you can do something simpler than what I said. You could just take these two pieces of the black hole and just glue them on the horizon sharply. Don't smooth out the gluing. Okay, so you just take two outer domains of outer communications and glue them on horizons, and then you have two sheets going out. That's sufficient insofar as checking that the Einstein's equation is satisfied.
I see. Yes.
It's a bit of a pain to work with it if you want to work with it for finding solutions. This is nicer because it smooths out the solution and picks up monodromy structures quite nicely.
I see. And so this setup, so can we have some analytical control for two-dimensional conformal field theory?
Yes. So this is the case. So in the first paper with Chandan and Loga, we actually worked out 2- and 3-point functions analytically in 2D CFT. So I've written the 2-point function, but the 3-point function is writable. It's not pleasant. It's some Meyer G function, but I can tell you what the answer is. It's in the paper. So
I see.
And I don't think there's any obstruction there to doing anything else. And in fact, you can even do something more exotic. This is what we've been doing with Julio to understand some of the general structures of how non-Gaussianities impact, say, when you have non-Markovian degrees of freedom. So we cooked up a toy model, and in that toy model, we can actually do calculations explicitly in ADS3.
Also, do you have also this difference of Markovian, non-Markovian also for this ADS3 case, two-dimensional?
No, because you see in ADS3, the graviton is not dynamic.
No, not a problem.
Yes.
No. It's peculiar to hire.
Yeah, yes. I could give you one more piece of intuition since I didn't want to mention it in the main part of the talk. This, if you look at these non-Markovian actions, if you stare at them for a while, you can show that you can map this non-Markovian action to a probe of a hyperscaling violating background. Okay, so people who studied, local criticality, they've worked out various examples of hyperscaling violating backgrounds. This is of that kind. Okay, because this is some very much
probing. So by using this degree of freedom, you're probing.
Exactly.
So maybe this correlation function maybe show some criticality.
Exactly. That's what. So basically, you can forget about this. You can think of non-Markovian fields in ADS3 as effectively probing some hyperscaling violating backgrounds of a conformally covariant 2D of a conformal symmetry in 2D broken to Lifshitz-like symmetry.
I see.
So we haven't explored that connection very fully, but it's spelled out in some detail in one of our papers.
I see. Thank you very much.
Okay, so is there any other question?
Excuse me, I have one question. So it's a kind of quick question. So at some points you computed 2-point function of primary operators, so OA and OD. So you show there's some relation between 2-point functions. Yeah, that's one. Yes.
Yes.
So what's the difference between OA and OD here?
Yeah. So, OA is O left plus O right over 2, and OD is O left minus O right minus O left. But let me say more physically what this relation says. So in the Schwinger-Keldysh construction, I labeled fields by which contour they lie on, left or right. Okay, so you get some relation of this kind. But this relation is actually much more familiar if I write it slightly differently, because the Schwinger-Keldysh is really computing correlators with some particular out-of-time ordering in a single theory. I don't have two theories. Okay, these labels are just a proxy for something else. So the proxy is the following. You can go back to the usual Schwinger-Keldysh construction, the Keldysh rules, which relate these OD-OD correlators and OA-OD correlators to the following. This is the expectation value of the anti-commutator at finite temperature, and this is the expectation value of the retarded Green's function, commutator. It's a theta function. And the fact that the anti-commutator is related to the commutator up to a Bose-Einstein factor is a statement of fluctuation dissipation theorem.
So is that a universal relation? So that's hold for any,
Yes, for 2-point functions, this is the universal fluctuation dissipation theorem that holds for any thermal correlators. Yes.
Okay, thank you very much.
If you want, you can derive it very straightforwardly. You can think of trace e to the minus beta h AB, and this you can write as trace B of t minus I beta. Let's say it's A at 0, t, B at t. E to the minus, sorry, I need to move. It's A at minus I beta, e to the minus beta h, B at t. I have passed the operator through the density operator, analytically continuing it to minus I beta and conjugated it. And now you can just take this relation and massage it. And after a little bit of massaging, you'll see that. And if you actually go to frequency domain, you can see that you get factor of e to the beta omega. And if you massage it appropriately, then you'll see that this correlator one combination gives you commutator, the other combination gives you anti-commutator.
So is it equal to say so-called KMS relation?
It is the KMS relation.
Oh, okay.
Yes. It is indeed the Kubo-Martin-Schwinger relation. Yes.
I see.
Yes,
Okay.
yes.
Thank you so much.
All right. So more. Oh, okay. Otherwise, let's send the Mukund again for the one to talk.
Thanks.